What if gravity is not just a force, but the quiet architect of time itself? Every orbit, every falling apple, every spinning galaxy obeys the same invisible rule. Mass bends space, and time follows. From the ticking of atomic clocks to the slow drift of planets, gravity shapes not only where things move, but how long moments last. Tonight, on Velorin Sleepy Space Mysteries, we will gently explore how gravity and time intertwine across the cosmos, from Newton's equations to Einstein's spacetime curvature, from black holes to expanding galaxies. This is not speculation. It is measurable in microseconds and light years. If calm scientific journeys like this help you relax, subscribe, like, turn on the notification bell, and consider joining our membership to support deeper explorations. And before we continue, tell me in the comments where you're listening from. Let's see how far this quiet signal travels across Earth. Now, let's begin. Long before relativity transformed how we think about space and time, the universe was already operating with remarkable precision. Even before ideas like curved space-time or black holes existed, scientists uncovered a quieter but profound truth. The same unseen force that pulls an apple toward the ground also guides the moon as it circles Earth. At the center of this insight is a simple rule, one that looks almost humble when written down but carries immense meaning. It can be spoken like this: the gravitational force equals a constant called g, multiplied by the first mass, multiplied by the second mass, all divided by the distance between them squared. In words, Newton's law of universal gravitation tells us that every object in the universe pulls on every other object. The strength of that pull grows when the objects are more massive, and it weakens rapidly as the distance between them increases. Tucked inside this relationship is the gravitational constant, g, a fixed number that sets the overall strength of gravity. Its value is about 6.674 times 10 to the power of minus 11, measured in newtons times square meters per square kilogram. It is an extraordinarily small number, so small it almost feels insignificant. And yet, this tiny constant quietly governs the motion of planets, the structure of solar systems, and even the slow dance of entire galaxies. With this single law, falling objects and planetary motion were unified. The force that draws a stone toward Earth is the same force that holds Earth in orbit around the Sun. There is no separate rule for the heavens. The moon circles us because gravity binds it. We circle the Sun for the same reason. Earth moves along its orbit at about 29.78 kilometers per second, covering nearly 940 million kilometers each year in a path so steady that our calendars can be built upon it. The moon travels around Earth at roughly 1 kilometer per second, completing its journey in about 27.3 days. These are not arbitrary motions. They are balances between gravitational attraction and inertial motion, between falling inward and moving forward. Kepler's earlier laws of planetary motion, once empirical descriptions of orbital patterns, found deeper meaning in Newton's framework. The elliptical orbits Kepler described arise naturally from the inverse square pull of gravity. The square of a planet's orbital period is proportional to the cube of its average distance from the Sun, a relationship that becomes inevitable when gravitational force and circular motion meet in equilibrium. In this clockwork universe, orbital periods are not mysteries. They are consequences. Distance sets the rhythm. Mass determines the tempo. Gravity does more than move objects. It creates predictability. Because the force depends on measurable quantities, mass and distance, the resulting motion becomes calculable. And from calculable motion comes measurable time. The Earth's steady orbit defines the year. The Moon's cycle defines the month. Even before mechanical clocks, the sky itself was a timekeeper. A pendulum, swinging under Earth's gravitational acceleration of approximately 9.8 meters per second squared, becomes a terrestrial echo of orbital motion. This period depends on gravity and length, not on the mass of the bob. In that gentle back and forth arc, gravity sets the beat. Yet even Earth's gravity is not perfectly uniform. At higher altitudes, farther from Earth's center, gravitational acceleration decreases slightly. A pendulum on a mountain swings just a fraction more slowly than one at sea level. These differences are small but measurable. They remind us that gravity's influence extends outward, thinning with distance according to that quiet inverse square. To escape it entirely, an object must reach about 11.2 kilometers per second, Earth's escape velocity. Below that speed, trajectories bend back toward home. Above it, a spacecraft can depart the planet's embrace, trading gravitational potential for freedom. Within Newton's universe, two principles preserve order: conservation of energy and conservation of angular momentum. As a planet moves closer to the Sun in its elliptical path, it speeds up. As it moves farther away, it slows down. Energy shifts between kinetic and potential forms, but the total remains constant. Angular momentum, the measure of rotational motion, remains steady as well, causing orbital speed to increase when distance decreases. These conservation laws act like invisible guardians, ensuring that motion remains consistent over centuries, over millennia. There is a calm inevitability in this system. Nothing drifts aimlessly. Every movement answers to mass and distance. Every orbit can be predicted with astonishing accuracy. For more than 200 years, Newton's equations described planetary paths so precisely that eclipses could be forecast centuries in advance. The universe appeared as an immense mechanism, its gears interlocking, its motion steady and comprehensible. And yet, even in this near-perfect clockwork, a faint irregularity whispered from the innermost planet. Mercury's orbit did not close upon itself exactly as predicted. Its perihelion shifted slightly more than Newton's theory allowed, by about 43 arcseconds per century. The discrepancy was tiny, less than a fraction of a degree over a lifetime, but persistent. Most of Mercury's precession could be explained by gravitational tugs from other planets, but not all. The remaining 43 arcseconds lingered as a subtle imperfection in an otherwise flawless system. For now, though, within Newton's framework, the cosmos remains a grand and measurable rhythm. Mass pulls, distance moderates, motion unfolds with patient consistency. In this mechanical harmony, gravity does not merely bind worlds together. It defines the cadence of time itself, turning celestial motion into the steady ticking of the universe. If we stay a little longer inside Newton's universe, we start to see that gravity and time are linked not by philosophy, but by machinery. Everything runs according to a simple rule. The gravitational force equals a constant number, called g, multiplied by the first mass and the second mass, and then divided by the square of the distance between them. In words, gravity grows stronger when masses are larger and weaker when objects are farther apart, and it weakens smoothly as distance increases. The gravitational constant itself is extremely small, about 6.674 times 10 to the minus 11 in standard units. But that small number is precisely what keeps gravity gentle and predictable, even when planets and stars are involved. Because this force follows an inverse square law, meaning distance is squared in the denominator, gravity never switches on or off suddenly. It fades gradually, continuously, and reliably. That smooth behavior is why planetary motion can be calculated centuries in advance and why planets trace calm, repeating paths instead of wild or collapsing ones. Earth's orbit is a perfect example. It travels around the Sun at about 29.78 kilometers per second, and that speed is not random. It is exactly the speed needed to balance the Sun's gravitational pull at a distance of roughly 150 million kilometers. If Earth moved noticeably slower, gravity would pull it inward. If it moved noticeably faster, it would drift outward into a wider orbit. Instead, Earth exists in a delicate balance, always being pulled toward the Sun and always moving sideways fast enough to miss it, endlessly falling and endlessly stable at the same time. This balance between inward pull and forward motion is the essence of orbit. The Moon demonstrates the same principle on a smaller scale. Traveling at about 1 kilometer per second around Earth, it is constantly being drawn inward by gravity, yet its sideways velocity keeps it circling rather than collapsing. In each case, gravity provides the centripetal acceleration required to curve motion into a closed path. The fact that the Moon completes an orbit in about 27.3 days and Earth completes one around the Sun in about 365 days is not coincidence. These periods emerge directly from gravitational strength and orbital radius. Kepler's third law, when expressed through Newton's mathematics, reveals that orbital time is mathematically tied to distance. The farther a planet is from the Sun, the longer its year, and the relationship follows a precise ratio. The square of the period grows with the cube of the distance. Time in this framework is written into space. On Earth, gravity also governs simpler rhythms. A pendulum clock depends on gravitational acceleration, approximately 9.8 meters per second squared at sea level. The period of a pendulum depends on the square root of its length divided by this acceleration. Change gravity slightly, and the period shifts slightly. At higher altitudes, where distance from Earth's center increases, gravitational acceleration decreases by a small fraction, and a pendulum runs just a little slower. Even the shape of Earth contributes. Because our planet is not a perfect sphere but slightly flattened at the poles, gravity varies subtly with latitude. These differences are small, but they demonstrate that timekeeping in a Newtonian world is ultimately rooted in gravitational strength. Energy conservation ensures that orbital motion remains steady over immense durations. As a planet approaches perihelion, where it is closest to the Sun, gravitational potential energy decreases while kinetic energy increases, causing the planet to speed up. As it recedes toward aphelion, kinetic energy decreases and potential energy increases, slowing the planet down. Yet the total energy remains constant. Angular momentum conservation adds another layer of order. Because no external torque significantly alters a planet's motion, the product of its mass, velocity, and orbital radius adjusts in such a way that the motion remains stable. These twin conservation principles act like cosmic bookkeeping systems, ensuring that nothing is lost and nothing appears from nowhere. Escape velocity provides another window into gravity's structure. To leave Earth permanently, an object must reach approximately 11.2 kilometers per second. This speed is derived directly from equating kinetic energy with gravitational potential energy. It represents the threshold at which forward motion overcomes the inward pull entirely. Rockets that achieve this velocity do not escape because gravity disappears, but because their energy exceeds the gravitational binding energy of Earth. Again, the mathematics is calm and exact. No mystery intervenes, only balance and threshold. For centuries, this framework described the heavens with astonishing precision. Planetary positions could be predicted far into the future. Comets returned on schedule. Tides rose and fell under the moon's influence. The universe appeared as a vast mechanical system, each component responding predictably to the gravitational influence of every other. It was as though the cosmos were a grand clock, and Newton had revealed the gears. And yet, in that serene mechanical rhythm, one small imperfection persisted. Mercury, closest to the Sun and therefore most strongly influenced by its gravity, did not move exactly as Newton's equations predicted. Its elliptical orbit slowly rotated, a motion known as precession. Most of this precession could be explained by the gravitational perturbations of other planets, but about 43 arcseconds per century remained unaccounted for. The discrepancy was tiny, less than 1/100th of a degree over a human lifetime, yet it refused to vanish. The clockwork universe ticked with extraordinary regularity, but one gear seemed ever so slightly misaligned. That small deviation did not shatter Newton's achievement. It only hinted that gravity might possess subtleties beyond the inverse square law. Still, within the Newtonian picture, the cosmos remains profoundly ordered. Mass determines attraction. Distance moderates strength. Motion unfolds in curves that can be drawn with equations and confirmed by observation. Timekeeping, whether through pendulums or planetary orbits, emerges from gravitational stability. The universe moves with quiet inevitability, each orbit a steady pulse in a vast mechanical heart. If you are still listening, still drifting through this measured clockwork of motion and mass, type 1 in the comments and let the rhythm continue. Within this Newtonian framework, something quietly profound emerges. Gravity does not merely move objects through space. It creates a universe where motion can be trusted. Predictability becomes the defining feature of reality. Once the masses and distances are known, trajectories unfold with calm obedience. The same equation that explains why a stone accelerates downward at about 9.8 meters per second squared also explains why Jupiter completes its orbit in nearly 12 Earth years and why Saturn takes almost 29.5. There is no hierarchy separating earthly physics from celestial mechanics. The falling apple and the circling planet are participants in the same universal law. This unity was revolutionary not because it was dramatic, but because it was serene. The heavens were no longer divine exceptions. They were extensions of the same quiet mathematics beneath our feet. The inverse square nature of gravity carries deep consequences. Because the force weakens with the square of distance, doubling the distance reduces gravitational pull to 1/4. This precise scaling ensures stable orbits are possible. If gravity weakened more slowly, orbital paths might spiral inward. If it weakened more rapidly, planets might drift away. The specific mathematical form of 1 divided by r squared creates a delicate balance that allows elliptical motion to repeat again and again. Kepler's second law, describing equal areas swept in equal times, becomes a statement about angular momentum conservation. As a planet approaches the Sun and its orbital radius shrinks, its velocity must increase so that the area swept over a given time interval remains constant. There is something almost musical about this compensation. Distance decreases, speed increases. Distance increases, speed decreases. The rhythm holds. Angular momentum itself is a measure of rotational persistence. In the absence of external torque, it cannot change. This is why a spinning ice skater rotates faster when pulling in their arms. On cosmic scales, the same principle governs planetary systems. As clouds of gas collapse under gravity to form stars and planets, tiny initial rotations become amplified. The resulting disks flatten and spin, conserving angular momentum while redistributing mass. Entire solar systems arise from this conservation principle combined with gravitational attraction. What appears as complex structure is, at its core, the inevitable outcome of simple rules applied consistently. Energy conservation provides another stabilizing thread. Total mechanical energy in an isolated gravitational system remains constant. Potential energy becomes kinetic energy and back again, but the sum does not drift. This is why orbits repeat in steady cycles instead of gradually gaining or losing speed without cause. Even slight perturbations from neighboring bodies can be calculated as small corrections layered onto the primary gravitational pull. Newton's equations allowed astronomers to discover Neptune not by seeing it directly, but by noticing slight deviations in Uranus's orbit and calculating where an unseen mass must reside. The universe revealed hidden objects because its motions were so reliable that even small irregularities stood out. Gravity also sets limits. Escape velocity, approximately 11.2 kilometers per second for Earth, defines the boundary between being bound and being free. This number is not arbitrary. It emerges from equating kinetic energy with gravitational potential energy. Achieve that speed, and an object can climb forever against Earth's pull, slowing as it rises but never returning. Fall short, and gravity eventually reclaims it. These thresholds demonstrate how Newton's mechanics translates directly into engineering reality. Every rocket launch is a negotiation with this gravitational barrier. Even tidal forces can be described within the same framework. Because gravity decreases with distance, the near side of Earth experiences a slightly stronger pull from the Moon than the far side. This differential force stretches our oceans, creating tides that rise and fall with predictable regularity. The same mathematics that governs planetary orbits governs the daily breathing of our seas. Gravity shapes not only the motion of worlds, but the pulse of coastlines. And yet, for all its elegance, Newton's system contains a quiet assumption that time flows uniformly everywhere. Seconds tick identically whether on Earth or near the Sun. Space is absolute, a fixed stage upon which masses interact. Within that assumption, the equations operate flawlessly for nearly every observable phenomenon of the 17th, 18th, and 19th centuries. The universe appears as a grand mechanical structure, its parts interacting instantaneously across distance through gravitational attraction. There is no delay in the transmission of force, no curvature in the stage itself. Space and time are passive backdrops. For generations, this worldview held. It predicted eclipses, guided navigation, and described the trajectories of comets with astonishing accuracy. The mechanical metaphor became dominant. The cosmos is clockwork, its gears turning in synchrony. But Mercury's lingering discrepancy of 43 arcseconds per century persisted as a faint imperfection. The anomaly was small, but its persistence suggested that something subtle lay beyond the inverse square law. Not a collapse of the system, but perhaps a deeper layer beneath it. Still, before any revision arrives, it is worth resting in the calm coherence of Newton's universe. Mass attracts mass. Motion curves accordingly. Energy and angular momentum guard stability. Orbital periods encode distance. Pendulums measure gravity's strength. Tides respond to lunar pull. Escape velocity marks the edge of planetary embrace. Everywhere we look, motion answers to measurable quantities. The cosmos hums with consistency, its mechanical rhythm steady and reassuring. And within that rhythm, time feels universal, steady, dependable. If you are still listening, still drifting through this precise and predictable clockwork of motion and mass, type 1 in the comments and let the steady rhythm carry you onward. As the Newtonian picture deepens, it becomes clear that what we are really describing is not just gravity, but a philosophy of motion. In this universe, causes are clear, forces are measurable, and outcomes unfold with quiet reliability. If you know the position and velocity of every object at a given moment, the future can, in principle, be calculated indefinitely. This determinism is not dramatic. It is steady. It is the reason astronomers could predict the return of Halley's Comet decades before it reappeared. It is why eclipses can be forecast centuries in advance, down to the minute. Gravity, in Newton's formulation, does not surprise. It governs. Consider again Earth's orbit. At approximately 29.78 kilometers per second, our planet travels fast enough to cover a distance equal to the circumference of Earth in just over 1 second. Yet this enormous speed feels imperceptible because it is constant and balanced by the sun's gravitational pull. The inward acceleration caused by gravity bends Earth's path continuously, preventing it from flying off into interstellar darkness. That acceleration, though much weaker than the 9.8 meters per second squared we experience at Earth's surface, is perfectly sufficient at 150 million kilometers of separation. The inverse square law ensures that at that distance, the Sun's mass exerts exactly the right curvature on Earth's motion to produce a nearly elliptical orbit. The Moon provides a closer and gentler demonstration. Orbiting at roughly 1 kilometer per second, it is perpetually falling toward Earth. If gravity vanished, the Moon would continue in a straight line into space. If its forward motion ceased, it would drop inward. Instead, the two motions coexist, forming a closed path. The concept of orbit within Newton's universe is simply continuous free fall combined with sideways motion. There is no need for hidden mechanisms. Only mass, distance, and velocity. The elegance of this framework extends beyond planets and moons. Binary star systems, where two stars orbit a common center of mass, obey the same equations. Even galaxies, with their billions of stars, can be modeled approximately through gravitational interactions governed by the same constant g. Though the scale grows immense, the law remains unchanged. That universality is the quiet triumph of Newton's insight. One equation bridges apple and asteroid, pendulum and planet. Pendulums themselves illustrate gravity's partnership with time. The period of a simple pendulum depends on the square root of its length divided by gravitational acceleration. On Earth's surface, where g is about 9.8 meters per second squared, a 1-meter pendulum swings back and forth in roughly 2 seconds. On the Moon, where gravity is weaker, the same pendulum would swing more slowly. Thus, timekeeping becomes location-dependent not because time itself changes, but because gravity defines the restoring force that regulates oscillation. Mechanical clocks depend on this stability. So do the orbital cycles that define years and months. Gravity establishes the metronome of celestial time. Conservation laws reinforce this reliability. Angular momentum prevents planets from collapsing into their stars without cause. Energy conservation ensures that without external influence, orbital parameters remain fixed. Even small deviations, such as gravitational interactions between planets, can be calculated as perturbations layered atop primary motions. The universe, in this view, resembles a grand equation continuously solving itself. Yet, embedded in this mechanical harmony lies a conceptual simplicity that would later be challenged. Newton's gravity acts instantaneously across distance. If the Sun were to vanish, Earth, according to classical mechanics, would feel the change immediately. Space itself is rigid and absolute, the stage upon which forces operate. Time flows evenly everywhere, independent of motion or gravitational strength. These assumptions were natural in an era before the finite speed of light had been fully integrated into physics. They worked extraordinarily well for centuries, but Mercury's orbit remained a whisper of incompleteness. The additional 43 arcseconds of precession per century could not be dismissed as measurement error. Astronomers searched for unseen planets, proposed slight modifications, and refined calculations. The discrepancy endured. It was small enough to preserve confidence in Newton's system, yet persistent enough to suggest that gravity's story might not be entirely finished. For now, however, we remain in the calm symmetry of classical mechanics. The cosmos appears ordered and comprehensible. Forces produce accelerations. Accelerations curve trajectories. Periods follow from distances. Escape velocity defines thresholds. Tides rise from differential pull. Every movement answers to an equation. The mechanical rhythm is steady, almost soothing. It invites trust in the predictability of nature. And in that predictability, time feels stable, uniform, shared by all observers. The clockwork universe ticks on without hesitation. If you are still listening, still drifting through this steady mechanical harmony of mass and motion, type 1 in the comments and let the rhythm continue guiding us forward. There is something deeply calming about remaining, for a final moment, inside Newton's clockwork universe. Here, nothing is mystical. Nothing bends or stretches invisibly. Space is steady. Time flows evenly. Gravity is a force, direct and measurable, connecting masses across distance with mathematical precision. The equation F equals gmm2/ our superscript 2 does not merely describe attraction. It encodes a universe where motion unfolds with clarity. Once positions and velocities are known, the future becomes an extension of the present, predictable and continuous. This predictability allowed humanity to transform astronomy from observation into calculation. When astronomers charted the positions of planets night after night, they were not just mapping wandering lights. They were tracing the consequences of gravitational interaction. The fact that Earth moves at about 29.78 kilometers per second around the Sun means that every second, we travel nearly 30 kilometers through space without sensing it. The Moon, moving at roughly 1 kilometer per second, completes its orbit in a steady 27.3 days, maintaining the same gravitational partnership year after year. These motions do not drift randomly because angular momentum preserves their structure. Torque would act whenever bulges were misaligned. Angular momentum would redistribute until misalignment vanished. The timescale may have spanned tens or hundreds of millions of years, but the direction was fixed from the beginning. Gravity is not creative in its goals. It is relentless in its methods. The Moon's synchronous rotation is simply what happens when a rotating satellite is given enough time in the presence of a stronger neighbor. And yet, the stillness we perceive is only partial. The Moon continues orbiting at about 1 kilometer per second. It continues receding at 3.8 centimeters per year. Earth continues slowing. The system continues evolving toward a deeper equilibrium that will not be reached for billions of years. What looks like a frozen configuration is actually a balanced exchange still unfolding, just at a pace far slower than human lifetimes can easily perceive. If you are still following this quiet mechanical unfolding of gravity's slow engine, we are approaching the final layer of this part. What this equilibrium means not only for the Moon, but for Earth's long-term stability and the geometry of our future sky. If we step back and look at the Earth-Moon system as a whole, What we see is not a frozen sculpture but a continuously adjusting mechanism governed by conservation laws. The moon's tidal locking was not the end of motion. It was the end of excess motion. It marked the point at which rotational kinetic energy had been reduced to the minimum required for stability at that orbital distance. The early moon spun in under 10 hours. Today it rotates once every 27.3 days. That dramatic slowdown represents an enormous transfer of energy. Rotational kinetic energy depends on angular velocity squared. Reducing spin by such a large factor required dissipating vast amounts of energy through internal friction over hundreds of millions of years. That energy did not disappear. Some became heat inside the moon, influencing crust formation and volcanic history. Some was transferred outward as angular momentum, increasing orbital radius. The process was mechanical, not symbolic. Gravity stretched, friction resisted, torque corrected. Time completed the sequence. Now consider the system today. The moon is in synchronous rotation, meaning its angular velocity of spin equals its angular velocity of orbit. The equality omega_spin equals omega_orbit defines the lock. But because the moon's orbit is not perfectly circular and because gravitational influences from the sun introduce small perturbations, the lock operates within a narrow band of oscillation. Libration allows us to see 59% of the lunar surface over time. That number alone reveals something important. Even perfect synchronization permits subtle movement. The moon rocks slightly because its orbit speeds up and slows down along its ellipse. Its rotational rate remains nearly uniform, creating small viewing variations. These are not failures of locking. They are refinements within it. Meanwhile, Earth continues evolving. Tidal friction in Earth's oceans dissipates roughly 3.7 terawatts of energy. That continuous dissipation slows Earth's rotation by about 1.7 milliseconds per century. The effect is tiny on human timescales but decisive on geological ones. Laser reflectors left during the Apollo missions confirm that the moon recedes at approximately 3.8 centimeters per year. Over 1 million years, that is 38 kilometers. Over 100 million years, 3,800 kilometers. The outward drift lengthens the moon's orbital period. Because synchronous rotation ties spin to orbit, the moon's rotational period lengthens as well. The lock persists, but the duration of both rotation and revolution slowly increases. This reveals a crucial point. Tidal locking does not freeze time. It links motions. As distance changes, the shared period changes. The equilibrium is dynamic. It adjusts continuously to the evolving geometry of the system. Angular momentum conservation governs the entire exchange. The total angular momentum of Earth's spin plus the moon's orbital motion remains effectively constant. As Earth loses rotational angular momentum, the moon gains orbital angular momentum. The redistribution is gradual but relentless. There is no external referee enforcing this balance. It arises automatically from Newton's laws and the physical reality of deformable bodies under gravitational stress. In the far future, if the sun's evolution did not intervene, Earth's rotation would continue slowing until 1 Earth day equals 1 lunar month. At that point, Earth would also become tidally locked to the Moon. Both bodies would rotate once per orbit, always showing the same face to each other. Tidal torques would vanish because no misalignment would remain to generate them. Energy exchange would approach zero. This configuration represents the minimum energy state for a gravitationally bound rotating pair. It is the logical conclusion of the same process that locked the Moon billions of years ago. But we do not live in that final state. We live in the middle of the story. The Moon's synchronization feels eternal because 4.5 billion years exceeds our intuitive grasp. Yet, from a mechanical perspective, it is a transitional phase in a long sequence of energy redistribution. The Earth-Moon system has not stopped changing. It has simply slowed to a pace that feels still. Gravity has acted as a patient sculptor, not by carving quickly, but by shaving away imbalance millimeter by millimeter, millisecond by millisecond. Angular momentum acts like a cosmic safeguard. When a planet moves closer to the Sun in its elliptical path, its orbital radius decreases, so its velocity must increase to keep angular momentum constant. This is why Earth travels slightly faster at perihelion than at aphelion. The conservation principle ensures that motion compensates for distance. No energy vanishes. It shifts form. Potential energy becomes kinetic energy and returns again in a quiet exchange. This continual transformation, governed by conservation laws, is what keeps orbits stable across centuries. Even the formation of planetary systems reflects this same mechanical inevitability. Vast clouds of gas collapse under their own gravity. As they contract, tiny initial rotations amplify, flattening the cloud into a spinning disk. From this disk, planets condense, inheriting angular momentum that keeps them circling their newborn star. What appears complex is the cumulative result of simple gravitational attraction and conservation principles applied over immense spans of time. The system organizes itself because gravity guides it toward equilibrium. And yet, within this serene determinism, gravity also defines limits. Escape velocity, approximately 11.2 kilometers per second for Earth, marks the boundary between remaining bound and departing permanently. This value emerges directly from equating kinetic energy to gravitational potential energy. It is not symbolic. It is exact. Rockets must exceed this threshold to free themselves from Earth's pull. Fall short and gravity reclaims them. This same reasoning applies on larger scales. Stars must retain sufficient mass to prevent material from escaping. Galaxies must hold enough gravitational cohesion to remain intact. Everywhere, gravity defines thresholds and boundaries. The predictability of this framework created immense confidence in classical physics. With Newton's equations, eclipses could be forecast centuries ahead. Comets could be tracked across generations. Even subtle perturbations in planetary motion could reveal unseen masses. Neptune was discovered not by direct observation, but because Uranus's orbit deviated slightly from prediction. By calculating the necessary gravitational influence, astronomers located a new planet. The clockwork was so precise that even minor irregularities became clues. Still, Mercury's anomalous precession of about 43 arcseconds per century persisted. Though tiny, it was measurable and consistent. Newton's equations explained nearly all of it through planetary perturbations, yet that remaining fraction resisted correction. The discrepancy was not catastrophic. It was delicate, a faint tremor in an otherwise perfect mechanism. It did not overthrow the system, but it suggested that gravity might not be entirely captured by the inverse square law alone. Yet even this imperfection underscores the strength of the Newtonian vision. The anomaly was visible precisely because the system was so reliable. If gravity were chaotic, such a small deviation would have gone unnoticed. Instead, the regularity of orbital motion made the discrepancy stand out. The universe was orderly enough that even fractions of arcseconds mattered. In this mechanical cosmos, time itself appears absolute. A second on Earth is the same as a second near the sun. Space provides a fixed stage, unaffected by the masses it contains. Gravity acts across distance without delay. Within this picture, the universe resembles an immense clock whose gears interlock across scales. From pendulums swinging under 9.8 meters per second squared of acceleration to planets racing through space at tens of kilometers per second, motion remains bound by the same quiet law. There is reassurance in this stability. The cosmos does not lurch unpredictably. It moves with measured rhythm. Each orbit repeats with gentle consistency. Each conservation law preserves balance. The falling apple and the circling moon obey the same principle. Mass shapes motion, and motion unfolds with mathematical grace. But at the edges of this serene clockwork, subtle cracks are beginning to appear. Mercury's precession is one. The finite speed of light, soon to challenge instantaneous force, is another. For now, though, Newton's universe remains a masterpiece of clarity, a grand mechanical symphony where gravity conducts and time keeps steady beat. If you have drifted this far through the steady rhythm of motion, mass, and measurable time, type 1 in the comments and let's continue onward into the next layer of gravity's story. Einstein's great revelation begins with a quiet shift in perspective. For centuries, gravity had been understood as a force, an invisible pull acting between masses across space. That description worked beautifully for falling apples and orbiting planets. But in 1915, with the completion of general relativity, gravity was reimagined not as a force at all, but as geometry. Space and time were no longer separate stages upon which events unfolded. They merged into a single fabric, spacetime. And this fabric was not rigid, could bend, stretch, and curve. The central insight can be spoken gently, without equations. Mass and energy tell spacetime how to curve, and curved spacetime tells matter how to move. This simple sentence replaces the idea of gravitational pull with something deeper. The sun does not reach out and tug on Earth. Instead, its mass reshapes the geometry around it, and Earth follows the straightest possible path within that curved geometry. To understand why this matters, begin with light. The speed of light in vacuum is approximately 300,000 kilometers per second. In Einstein's universe, nothing travels faster, not even gravity itself. changes in gravitational influence propagate at this finite speed. That alone already departs from Newton's instantaneous force. But the deeper change lies in how motion is defined. In flat spacetime, a freely moving object travels along a straight line. In curved spacetime, that straight line becomes a curve when viewed from outside. The object is not being pushed. It is simply following geometry. Imagine a clock resting on Earth's surface. Now imagine an identical clock placed aboard a satellite orbiting about 20,200 kilometers above Earth, where GPS satellites reside. According to general relativity, the clock higher up, experiencing weaker gravity, ticks slightly faster. The difference is small but measurable, on the order of tens of microseconds per day. In fact, GPS satellites require a correction of about 38 microseconds per day when both gravitational time dilation and motion are accounted for. Without that correction, navigation systems would drift by kilometers within hours. Even between Earth's surface and low orbit, atomic clocks differ by nanoseconds per day. These are not theoretical curiosities. They are engineering necessities. Gravity bends time itself. The deeper you are in a gravitational well, the slower time flows relative to someone farther away. This effect is called gravitational time dilation, and it has been confirmed repeatedly with atomic clocks placed at different altitudes. Time is no longer absolute. It stretches and compresses depending on curvature. The geometry of spacetime is encoded mathematically in Einstein's field equations, but their conceptual meaning is more important than their symbols. Energy, mass, pressure, and momentum contribute to curvature. The resulting curvature determines the paths of planets, light beams, and even clocks. In weak fields, such as around Earth, the curvature is gentle. In stronger fields, it becomes dramatic. Consider a neutron star. Imagine compressing about 1.4 times the mass of our Sun into a sphere roughly 20 kilometers in radius. The density becomes almost unimaginable. In such an environment, spacetime curvature is extreme. A clock on the surface of a neutron star would tick significantly slower than one far away in interstellar space. Light escaping from that surface would be redshifted, stretched to longer wavelengths as it climbs out of the gravitational well. Push this compression further and you approach a black hole. Every mass has an associated Schwarzschild radius, a critical radius proportional to its mass. If an object is compressed within that radius, an event horizon forms. For Earth, that radius would be only about 9 millimeters. For the Sun, roughly 3 kilometers. Inside this boundary, curvature becomes so intense that all paths lead inward. The event horizon is not a solid surface. It is a geometric boundary in spacetime. From the perspective of a distant observer, an object falling toward a black hole appears to slow down as it approaches the horizon. This clock seems to tick more and more slowly. Light from it becomes increasingly redshifted. Eventually, it fades from view, as though time itself has frozen at the edge. Yet for the falling object, time proceeds normally. It crosses the horizon in finite proper time. This difference in perspective reveals how profoundly time depends on gravity. One observer's frozen moment is another observer's continuous experience. Even before black holes were observed directly, general relativity made bold predictions that could be tested. One of the earliest confirmations came during the solar eclipse of 1919. During totality, stars positioned near the sun in the sky became visible. According to Einstein's theory, their light should bend as it passed near the sun's mass. The measured deflection matched the prediction. Light, though massless, follows the curvature of spacetime. This bending of light, now called gravitational lensing, is observed routinely today. Entire galaxies act as lenses, distorting and magnifying light from objects behind them. Arcs and rings appear in telescope images, silent evidence that geometry itself is curved. The implications are both vast and intimate. Vast, because spacetime curvature shapes galaxies, black holes, and cosmic structure. Intimate, because the ticking of a clock on your wrist depends ever so slightly on Earth's mass beneath your feet. Gravity does not merely guide falling stones or orbiting moons. It defines the rhythm of time. Near massive objects, seconds stretch. Far from gravity, they flow more quickly. There is no universal clock governing the cosmos. Each path through spacetime carries its own measure of duration. In strong gravitational fields, this stretching becomes extreme. Near a black hole's event horizon, time dilation grows without bound relative to distant observers. In weaker fields like Earth's, the effect is subtle but measurable. Across all scales, the principle remains. The presence of mass reshapes both space and time. Einstein's revelation replaces force with form. Instead of invisible pulls, there is curvature. Instead of absolute time, there is local time shaped by gravity. Planets follow geodesics. Light curves. Clocks disagree. And all of it unfolds within a universe where geometry is dynamic and responsive. The cosmos is not a rigid stage. It is a flexible architecture, continuously molded by energy and mass. As you rest and imagine this vast geometry, consider that every object, including you, traces a path through curved spacetime. Your seconds are not identical to those far above Earth or deep near a neutron star. Time flows differently depending on gravity, and yet, within your local frame, it feels steady and calm. If you are still awake and traveling gently through spacetime, type 2, and let me know you are still drifting along this quiet curvature of the cosmos. Einstein's insight becomes even more profound when we linger on the idea that space and time are not separate entities, but woven together into a four-dimensional continuum. Before general relativity, time was assumed to tick uniformly everywhere, like a master clock for the universe. But in curved spacetime, time is local. It depends on where you are and how deep you sit within gravity's influence. Imagine two observers, one standing at sea level and another on a mountain peak. The one higher up is slightly farther from Earth's mass. The curvature there is slightly weaker. As a result, their clock ticks slightly faster. The difference is tiny, mere nanoseconds per day, but measurable with modern atomic clocks. This is not a flaw in the clocks. It is a feature of the universe. Time itself is stretched by gravity. Now extend this idea outward. GPS satellites orbit Earth at roughly 20,200 kilometers in altitude. At that height, gravity's pull is weaker than on the surface. Their onboard atomic clocks tick faster due to reduced gravitational time dilation, yet also slightly slower because of their orbital speed, which introduces special relativistic time dilation. When both effects are combined, engineers must apply a correction of about 38 microseconds per day. Without that correction, positioning errors would accumulate rapidly, and navigation systems would fail. The quiet functioning of modern technology is daily confirmation that gravity bends time. The geometry of spacetime does not merely curve around massive objects. It determines motion itself. In this framework, what we once called gravitational force is replaced by geodesics, the straightest possible paths in curved geometry. A planet orbiting a star is not being pulled inward by a mysterious attraction. It is following a natural path through warped spacetime. The curvature created by the star guides that motion as inevitably as a valley guides a river. The deeper the curvature, the more dramatic the effects. Consider again the Schwarzschild radius, the critical boundary around a mass where escape velocity equals the speed of light, approximately 300,000 kilometers per second. If mass is compressed within this radius, an event horizon forms. For the Sun, this radius would be about 3 kilometers. For a neutron star, already only about 20 kilometers across yet holding roughly 1 point for solar masses, the curvature is immense but not yet sufficient to form a black hole. On the surface of such a neutron star, time flows significantly slower than it does far away. Light climbing outward loses energy, stretching into longer wavelengths. The gravitational redshift is measurable and real. If collapse continues and the Schwarzschild radius is crossed, a black hole forms. At the event horizon, something extraordinary happens from the perspective of a distant observer. An infalling clock appears to slow down as it approaches the horizon. Its ticks become farther apart. Its light becomes more redshifted, dimmer and dimmer. To the distant observer, the clock never quite crosses the boundary. It seems frozen in time. Yet for the traveler falling inward, nothing peculiar occurs at the horizon itself. Their own clock continues normally. They cross the boundary in finite proper time. This duality reveals how relative time truly is. The phrase "time freezes at a black hole" is only meaningful relative to someone far away. Locally, time always feels normal. It is comparison across different gravitational potentials that reveals the stretching. Even light is subject to this geometry. During the solar eclipse of 1919, starlight passing near the Sun was observed to bend by precisely the amount Einstein predicted. This bending was not caused by a force tugging on photons. It occurred because space-time around the Sun was curved, and light followed that curvature. Today, gravitational lensing is observed on vast scales. Entire galaxies bend the light of more distant galaxies, creating arcs and rings in telescope images. In these cosmic lenses, geometry itself becomes visible. The curvature of spacetime leaves fingerprints in the sky. At even greater extremes, near black holes, light can orbit temporarily within a region known as the photon sphere. Paths that would be straight in flat space become loops in curved space. Geometry replaces force entirely. The universe becomes an evolving landscape of curvature, shaped by mass and energy at every scale. What makes this revelation so calming, perhaps, is its consistency. The same principle governs falling apples, orbiting satellites, neutron stars, and black holes. Mass energy shapes geometry. Geometry shapes motion. And within that geometry, time is woven inseparably into space. Seconds are not universal. They are local expressions of curvature. When you sit quietly on Earth, your time flows according to Earth's mass and your position within its gravitational well. If you could hover near a neutron star, your seconds would stretch relative to those far away. If you could approach the event horizon of a black hole and somehow survive, you would witness the distant universe race forward while your own time slowed relative to it. General relativity does not just describe exotic cosmic objects. It quietly informs the structure of everyday reality. Every orbiting satellite, every redshifted photon, every gravitational wave passing silently through space is a reminder that gravity is geometry. And geometry bends time. The universe is not ticking to a single rhythm. It is a symphony of local clocks, each following its own path through curved spacetime. And yet, within your immediate frame, the flow feels smooth and continuous. That gentle normalcy is itself part of the geometry. If you are still awake, still drifting through this curved architecture where gravity shapes the passage of moments, type 2 and continue traveling softly through space-time. If we follow Einstein's revelation to its furthest implications, we begin to see that gravity is not merely something that bends the paths of planets or slows the ticking of clocks. It shapes the very structure of causality, defining what events can influence one another and how signals travel through the universe. Because gravity propagates at the speed of light, about 300,000 kilometers per second, changes in curvature ripple outward no faster than light itself. This preserves a cosmic speed limit. No influence outruns space-time. Even gravity must obey the geometry it creates. In this sense, the universe is self-consistent, a vast structure where curvature and motion remain in dialogue. One of the most elegant confirmations of this dialogue comes from the existence of gravitational waves. When massive objects accelerate asymmetrically, such as two neutron stars spiraling toward one another, they disturb spacetime itself. These disturbances propagate outward as ripples in geometry. They are not waves traveling through space. They are waves of space. When such a ripple passes through Earth, it stretches and compresses distances by an almost unimaginably small amount, less than the width of a proton across kilometers of detector arms. Yet even this tiny shift can be measured. These waves move at light speed, reinforcing that gravity is not instantaneous action at a distance, but dynamic curvature evolving through time. The same framework that predicts gravitational waves also predicts the extreme behavior near black holes. As matter collapses inward, curvature increases. If sufficient mass is compressed within its Schwarzschild radius, an event horizon forms. From the outside, we see a boundary beyond which signals cannot return. The escape velocity at that radius equals the speed of light. Nothing slower can climb back out. This is not because of an invisible barrier, but because all possible paths through spacetime inside that boundary curve inward. Even light, which always travels locally at 300,000 kilometers per second, cannot find a trajectory that leads outward once inside. Geometry seals the region off. Near this boundary, time dilation becomes extraordinary. Suppose an astronaut could hover just above the event horizon of a black hole, supported by immense thrust. To distant observers, their clock would appear to slow dramatically. A single hour for the astronaut might correspond to years passing far away. The deeper the gravitational well, the slower time flows relative to distant regions. This is not science fiction speculation. It is a direct consequence of the equations of general relativity. And it applies not only to black holes but to any massive body, though usually with much gentler effect. Even on Earth, gravitational time dilation is real. Atomic clocks placed at different altitudes tick at slightly different rates. The differences are measured in nanoseconds per day, but they accumulate. Modern metrology laboratories confirm these shifts routinely. What is astonishing is not the size of the effect, but its inevitability. The universe has no universal now. Two observers separated by gravitational potential do not share identical durations. Time becomes part of the terrain. Consider again neutron stars, those collapsed remnants of massive stars. With roughly 1.4 times the mass of our Sun compressed into a sphere about 20 kilometers across, their surface gravity is immense. If you stood upon such a surface, your clock would tick noticeably slower compared to one far away in interstellar space. Light escaping from that surface would be strongly redshifted. The curvature is intense but not infinite. Only when collapse continues beyond a critical radius does the event horizon form and curvature deepen without bound toward the singularity predicted by classical theory. Black holes, therefore, represent the ultimate curvature in spacetime. Yet even here, general relativity maintains coherence. The equations predict the bending of light, the slowing of time, the orbital dynamics of stars near galactic centers. Observations of stars orbiting invisible massive objects confirm that supermassive black holes reside at the centers of galaxies. Their masses shape the motion of entire stellar systems. Geometry on such scales determines galactic architecture. And yet the same principle governs a falling apple. Mass energy tells spacetime how to curve. Spacetime tells matter how to move. There is a profound simplicity in this reciprocity. The complexity of cosmic phenomena, lensing arcs across billions of light years, the quiet drift of GPS satellites, the shimmering redshift of photons escaping dense stars, all arise from the same geometric rule. Gravity is not something acting within spacetime. It is spacetime acting. Time itself becomes elastic, stretched by depth in gravitational wells. The deeper you descend, the slower your local clock runs relative to those higher up. If gravity vanished entirely, spacetime would flatten, and clocks everywhere would tick in uniform relation. But in our real universe, mass is everywhere. Stars, planets, galaxies all contribute to curvature. The cosmos is a dynamic tapestry of wells and slopes. We move through it continuously, following geodesics whether we are aware of them or not. Even standing still on Earth, you are deviating slightly from your natural freefall path, held up by the ground beneath you. In orbit, astronauts feel weightless because they are following geodesics through curved spacetime. Weight is resistance to geometry. Freefall is surrender to it. In this view, gravity becomes quieter than force. It becomes architecture. It shapes the intervals between heartbeats as subtly as it shapes the motion of galaxies. The seconds you experience are local expressions of curvature. Somewhere near a neutron star, those seconds stretch more slowly. Near a black hole's edge, they nearly stall relative to distant observers. And yet everywhere locally time feels steady. That is the elegance of relativity. It preserves local normalcy while revealing global variation. So as you drift through this understanding, notice the calm coherence of it all. No invisible hands pulling objects across empty space. Only geometry, curved by mass, guiding motion and shaping duration. The universe is not rigid. It is responsive, and time itself bends softly wherever gravity resides. If you are still awake, still journeying along these curved paths where mass shapes moments and seconds stretch in quiet proportion to gravity, type 2 and continue traveling gently through space-time. As we continue deeper into Einstein's revelation, it becomes clear that gravity does more than bend the trajectories of planets or stretch the ticking of clocks. It defines the very limits of experience. In a universe governed by curved space-time, distance and duration are intertwined. Every object traces what physicists call a world line, a path through four-dimensional space-time. That path is shaped not by force in the traditional sense, but by curvature created by mass and energy. The result is a cosmos where geometry quietly governs destiny. Consider the simple idea of falling. In Newton's description, an apple drops because Earth pulls on it with a force proportional to its mass. In Einstein's description, the apple is following the straightest possible path through curved spacetime. The ground beneath it prevents that natural motion, pushing upward and creating the sensation we interpret as weight. This reframing seems subtle, yet it changes everything. It means that in orbit, astronauts feel weightless not because gravity has disappeared, but because they are no longer resisting their natural geodesic path. They are moving freely within curved spacetime. The equivalence between acceleration and gravity, which Einstein recognized early on, becomes central here. Inside a sealed, accelerating spacecraft, you would feel pressed against the floor exactly as if gravity were pulling you downward. Inside a freely falling elevator, you would float weightlessly, unable to distinguish falling from deep space drift. This equivalence led Einstein to conclude that gravity is not a conventional force. It is the manifestation of curved geometry. Once this insight is accepted, the behavior of time becomes less mysterious. If space and time form a unified fabric, then bending one inevitably bends the other. Near massive objects, time flows more slowly relative to regions of weaker gravity. This is gravitational time dilation, It has been confirmed repeatedly with atomic clocks placed at different heights above Earth's surface. Even differences of a few centimeters can produce measurable variations when clocks are precise enough. Time is sensitive to altitude because altitude determines gravitational potential. The deeper you are in a gravitational well, the slower your clock runs relative to someone higher up. At modest scales, such as Earth's surface compared to orbit, the difference amounts to nanoseconds per day. At the altitude of GPS satellites, around 20,200 kilometers, the combined relativistic corrections total roughly 38 microseconds per day. That may sound insignificant, yet without correcting for it, navigation systems would drift disastrously. The quiet accuracy of your phone's positioning system is a daily affirmation that gravity bends time. Move to stronger gravitational environments and the effect intensifies. A white dwarf star, about the size of Earth but containing a mass comparable to the Sun, produces substantial time dilation at its surface. A neutron star, roughly 20 kilometers in radius yet holding around 1.4 solar masses, warps spacetime even more dramatically. Light escaping from its surface is significantly redshifted. Seconds there are not equal to seconds far away. If one could stand safely on such an object, which is physically impossible due to tidal forces, the passage of time would feel normal locally, yet distant observers would measure it as slower. Push further still and black holes emerge. Their defining boundary, the event horizon, marks the region where the escape velocity equals the speed of light, approximately 300,000 kilometers per second. The Schwarzschild radius determines this boundary, proportional to mass. Once matter collapses within this radius, all paths lead inward. From the perspective of distant observers, anything approaching the horizon appears to slow, its clock ticking ever more gradually, its emitted light increasingly redshifted. It seems to freeze at the edge. Yet for the falling observer, time proceeds without interruption. They cross the horizon in finite proper time. This divergence of perspectives reveals the relativity of duration itself. There is no single universal tempo. Each observer carries their own clock along their world line. Even causality, the ordering of events, is embedded in this geometry. Light cones define which events can influence others. Because gravitational changes propagate at the speed of light, no information outruns spacetime's curvature. The universe maintains consistency by enforcing this limit. The same principle that caps the speed of light also governs gravitational waves, ripples in spacetime produced by accelerating masses. These waves travel at light speed, stretching and compressing distances as they pass. They confirm that spacetime is dynamic, capable not only of curvature but of vibration. Einstein's field equations encode all of this in compact mathematical form, yet their conceptual message remains simple. Mass energy tells spacetime how to curve. Spacetime tells matter how to move. Every orbit, every fall, every bent beam of light, every delayed clock is a consequence of this mutual relationship. The cosmos is not a static container holding objects. It is an evolving structure shaped continuously by what it contains. Time, once thought universal and absolute, becomes personal and contextual. Your heartbeat marks seconds defined by Earth's gravity. A clock in deep interstellar space would tick slightly faster. A clock near a neutron star would tick slower still. Near a black hole's edge, relative time stretches towards stillness from an external perspective. Yet everywhere, locally, time feels steady. This is perhaps the most soothing aspect of relativity. Although globally flexible, locally it preserves calm continuity. The bending of time does not disrupt experience. It only reveals that experience depends on position within gravity's architecture. And so the revelation is complete. Gravity is not an invisible hand pulling masses together. It is the curvature of spacetime itself. It shapes not only where objects travel, but how long moments last. From the smallest measurable nanosecond differences between clocks on Earth and in orbit, to the near-frozen time at the edge of a black hole, the message remains consistent. Time flows differently depending on gravity, and within that gentle variation lies the quiet architecture of the cosmos, steady, coherent, and profoundly interconnected. If you are still awake, still drifting along these curved world lines through bending time, type 2 and continue traveling softly through spacetime. Across the largest scales we can measure, gravity does not disappear. It simply changes character. In the quiet between galaxies, where distances stretch beyond imagination, gravity still writes the rules, but it now shares the stage with expansion itself. Nearly a century ago, astronomers began noticing something subtle but profound. Galaxies were not merely drifting randomly. They were receding from us in proportion to their distance. This relationship, now described by the Hubble expansion rate of roughly 70 kilometers per second per megaparsec, means that for every megaparsec, about 3.26 million light-years, a galaxy is farther away. Its recessional velocity increases by about 70 kilometers per second. At 10 megaparsecs, 700 kilometers per second. At 100, 7,000 kilometers per second. This is not because galaxies are flying through space like shrapnel from an explosion. It is because space itself is stretching. The fabric that Einstein described, spacetime, is expanding. And within that expansion, gravity still operates locally, binding stars into galaxies and galaxies into clusters, even while the larger cosmic backdrop grows ever wider. When we look outward far enough, we are looking backward in time. The observable universe has a radius of about 46 billion light-years, even though its age is approximately 13.8 billion years. That apparent contradiction arises because space has expanded while light was traveling. The photons we detect today from the cosmic microwave background began their journey when the universe was only about 380,000 years old. That radiation now fills all of space at a temperature of about 2.7 Kelvin, a faint thermal whisper cooled by billions of years of expansion. It is gravity's early imprint, frozen into the sky. In those first moments after the Big Bang, matter was not evenly distributed. Tiny fluctuations in density, 1 part in 100,000, existed within the primordial plasma. Gravity amplified those slight imbalances. Regions slightly denser pulled in more matter. Over millions of years, then hundreds of millions, clouds collapsed. The first stars ignited. galaxies formed. Gravity, patient and persistent, turned irregularities into structure. Yet visible matter, the atoms in stars, gas, dust, and planets, accounts for only a fraction of the gravitational influence we observe. Galaxies rotate too quickly at their edges. Clusters hold together more tightly than luminous matter alone can explain. This invisible mass, known as dark matter, exerts gravitational pull without emitting light. It forms vast halos around galaxies, scaffolding upon which cosmic structure assembled. Without dark matter's gravitational influence, galaxies as we know them would likely never have formed. And still, expansion continues. In the late 1990s, observations of distant supernovae revealed something unexpected. The expansion of the universe is accelerating. Instead of slowing under gravity's pull, distant galaxies are receding faster over time. The cause appears to be dark energy, a pervasive component of spacetime itself that acts repulsively on cosmic scales. If gravity pulls inward, dark energy pushes outward. On small scales, within galaxies, within clusters, gravity wins. On the largest scales, beyond superclusters, dark energy dominates. The long arc of time bends between these two influences. Consider our own star. The Sun has a total expected lifetime of about 10 billion years. It formed roughly 4.6 billion years ago and will continue fusing hydrogen for another 5 billion or so. Gravity compresses its core, raising temperatures high enough for nuclear fusion to occur. Outward radiation pressure balances inward gravitational collapse. This equilibrium hydrostatic balance is gravity working not as destruction, but as structure. When the Sun exhausts its hydrogen, gravity will once again dominate, compressing the core until new fusion stages ignite. Eventually, it will shed its outer layers and settle as a white dwarf, a dense remnant slowly cooling across trillions of years. On larger scales, the same principle applies. Stars form because gravity pulls gas clouds together. Black holes form when gravity overwhelms all opposing forces. Supermassive black holes anchor most galaxies, including our own. They are regions where spacetime curvature becomes so extreme that even light cannot escape. Gravitational collapse represents one possible end state of matter. But cosmic expansion offers another trajectory entirely. If dark energy continues to dominate and remains constant, the universe may approach what cosmologists call heat death. Over vast stretches of time, trillions upon trillions of years, star formation will cease as gas is exhausted. Existing stars will burn out. Galaxies will drift beyond one another's observable horizons. Black holes will slowly evaporate through quantum processes over unimaginable durations. Temperature differences will fade. Energy will spread evenly. Gravity will still exist, but with little structure left to shape. Equilibrium will be nearly complete. Not dramatic destruction, but gradual fading. Yet even in this distant future, gravity remains the architect of every stage. It births stars from cold clouds. It binds planetary systems. It governs orbital motion. It collapses massive cores into neutron stars and black holes. It sculpts galaxies and organizes clusters across millions of light-years. It also competes with expansion, defining the ultimate geometry of the cosmos. The tension between gravitational attraction and cosmic expansion determines whether the universe slows, coasts, or accelerates. Present measurements suggest acceleration will persist. Galaxies not gravitationally bound to us will eventually disappear beyond our observable horizon, their light stretched beyond detection. The night sky in a far future epoch may grow darker, not because stars have vanished locally, but because distant galaxies have receded irretrievably. Still, within gravitationally bound systems like our local group, gravity will hold sway long after expansion isolates us. The Milky Way and Andromeda are expected to merge in about 4 billion years, drawn together despite cosmic expansion. On those scales, gravity overcomes the stretching of space. This contrast is profound. On one hand, gravity collapses matter into dense singularities. On the other, expansion thins matter into near-nothingness. Collapse and dispersal, both shaped by the same fundamental equations of spacetime curvature. Einstein's field equations allow for both behaviors. Geometry responds to energy density. When density dominates locally, gravity binds. When dark energy dominates globally, space expands. The universe is not static. It evolves through phases where gravity assembles complexity and expansion dilutes it. Through all of it, time itself is guided by curvature. In strong gravitational fields, time slows. In expanding space, wavelengths stretch and clocks separate. The age of the universe, 13.8 billion years, is measured through models that combine expansion rate, matter density, radiation remnants, and gravitational dynamics. Every estimate relies on gravity's imprint. From the 2.7 Kelvin afterglow of the cosmic microwave background to the distribution of galaxies across 46 billion light-years, gravity threads each scale together. It is present in the ticking of atomic clocks corrected for gravitational time dilation. It is present in the life cycle of stars. It is present in the vast recession of galaxies. It shapes the beginning of structure and the distant possibility of equilibrium. Gravity is not merely a force acting between objects. It is the quiet geometry within which time unfolds. It binds the small and governs the large. It shapes both the birth of stars and the ultimate fate of cosmic time. Across scales from kilometers to billions of light-years, from seconds to trillions of years, gravity is the thread stitching moments together. If you've reached this final stretch of our quiet journey through gravity and time, gently type 3 in the comments. A small signal across space, confirming that tonight you traveled from falling apples to the far horizon of the expanding universe. If we extend our view even further along the arc of cosmic time, gravity begins to reveal itself not only as a sculptor of structure, but as a regulator of destiny. The expansion rate we measure today, about 70 kilometers per second per megaparsec, is not merely a number in a textbook. It is a measure of how quickly separation grows between regions of spacetime that are no longer gravitationally bound. A galaxy 1 megaparsec away recedes at roughly 70 kilometers per second. At 10 megaparsecs, the recessional velocity approaches 700 kilometers per second. At 107,000. Beyond a certain scale, recession exceeds the ability of gravity to counteract it. Yet within clusters of galaxies, within the gravitational embrace of dark matter halos, expansion is effectively cancelled. The local group remains intact. The Milky Way and Andromeda move toward each other at about 110 kilometers per second, not apart. Gravity dominates locally because density dominates locally. This dual behavior, binding here, separating there, illustrates the layered structure of cosmic influence. The universe is approximately 13.8 billion years old, but its future stretches vastly longer. In about 5 billion years, the Sun will exhaust hydrogen in its core. Gravity will compress the core until helium fusion begins, and the outer layers will swell into a red giant, possibly engulfing Mercury and Venus. Eventually, the Sun will shed its outer layers into a planetary nebula, leaving behind a white dwarf roughly the size of Earth, but containing about half the Sun's current mass. That remnant will cool slowly for trillions of years. Gravity will hold it together through electron degeneracy pressure, a quantum mechanical resistance to further collapse. On even longer timescales, star formation across the universe will decline. Gas reservoirs are finite. Already, many galaxies convert gas into stars more slowly than in the past. In perhaps 100 billion years, most star formation will cease. The brightest stars will have long since died. Red dwarfs, small and efficient, may persist for trillions of years, fusing hydrogen at a slow, steady rate. Gravity will continue balancing fusion in those small stars, maintaining hydrostatic equilibrium. But eventually, even they will fade. Black holes, formed from stellar collapse and galactic centers, will dominate the mass budget of gravitationally bound systems. These black holes represent gravity in its most concentrated form. Yet even they are not eternal. Through quantum effects near the event horizon, black holes radiate extremely faint energy. A stellar mass black hole would take on the order of 10 to the power of 67 years to evaporate. Supermassive black holes, containing millions or billions of solar masses, would persist for around 10 to the power of 100 years or more. These timescales dwarf the current age of the universe by incomprehensible factors. Still, the direction is toward equilibrium. Heat death does not imply sudden catastrophe. It describes a gradual approach to maximum entropy, where temperature differences vanish and usable energy becomes scarce. Gravity initially creates structure by amplifying density differences. It turns uniform gas into stars and galaxies. But as expansion stretches space and as stars exhaust nuclear fuel, gravitational potential energy becomes harder to convert into new complexity. The universe trends toward uniformity. Dark energy plays a decisive role here. Observations indicate that roughly 70% of the cosmic energy density is dark energy, about 25% dark matter, and only about 5% ordinary matter. If dark energy remains constant in strength, expansion will continue accelerating. Distant galaxies will cross an event horizon of sorts, not a black hole horizon, but a cosmological one. Their light will be stretched to wavelengths so long that it becomes undetectable. Future observers in 1 trillion years, residing within a merged Milky Way Andromeda remnant, might see only their local galaxy. The broader cosmic web would lie beyond observational reach. Gravity will still bind their galaxy, but the larger universe will appear empty and static. In that far future, the cosmic microwave background, now at 2.7 Kelvin, will have cooled to nearly absolute zero, its wavelength stretched beyond detection. The memory of the early universe will fade into redshifted obscurity. Yet gravity's imprint will remain embedded in the motions of stars, in orbital dynamics, in the remnants of collapsed cores. It is remarkable that the same principle governing a falling object near Earth, acceleration of about 9.8 meters per second squared, also governs the growth of galaxy clusters millions of light-years across. Scale changes, equations remain. Gravity is described by the curvature of spacetime, and that curvature responds to mass-energy distribution everywhere. When density was high in the early universe, gravity slowed expansion. As expansion diluted matter density, dark energy's relative influence grew. The competition shifted. If dark energy were absent, gravity might eventually halt expansion and reverse it, leading to a recollapsing universe. Current measurements, however, favor continued acceleration. The cosmos appears destined not for collapse, but for thinning isolation. And still, within bound systems, gravity preserves order. Planets orbit stars. Stars orbit galactic centers. Even as intergalactic distances grow, local gravitational systems remain coherent islands in an expanding sea. This layered behavior reveals gravity's adaptability. It can collapse matter into black holes where spacetime curvature becomes extreme, or maintain delicate orbital resonances over billions of years. It can amplify primordial fluctuations into galaxies, or sustain white dwarfs against further collapse for trillions of years. In every epoch, gravity shapes time's direction by shaping energy flow. The birth of a star marks gravity converting potential energy into radiation. The death of a star marks gravity reclaiming dominance. The long cooling of stellar remnants marks gravity maintaining structure in silence. Across 46 billion light-years of observable radius, across 13.8 billion years of cosmic history, gravity has remained the consistent thread. It guided the first clumping of matter after the Big Bang. It determined when and where stars ignited. It governs the slow merger of galaxies. It will dictate the final evaporation of black holes. Even as expansion accelerates, it is gravity that defines what remains bound and what drifts away. In that sense, gravity does not oppose time. It defines time's architecture. Without gravity, there would be no stars to measure years, no planets to count days, no structure to anchor memory. Gravity creates clocks by creating systems stable enough to tick. And as the universe ages toward equilibrium, gravity's role shifts from builder to keeper of remnants. It holds what can be held. It releases what cannot. If you are still here at this distant horizon of thought, having followed gravity from cosmic dawn to far future equilibrium, gently type 3 in the comments. A small signal that you reached the end of tonight's quiet cosmic journey. There is something almost paradoxical about the long future shaped by gravity. In the early universe, gravity was the engine of complexity. It gathered hydrogen and helium into the first luminous stars. It assembled galaxies into spirals and ellipticals. It wove the vast cosmic web, stretching across hundreds of millions of light-years, where filaments of dark matter guided visible matter into glowing clusters. Gravity thrived on imbalance. Tiny density fluctuations in the young universe, imprinted when the cosmos was less than 1,000,000 years old, became seeds of structure precisely because gravity amplifies difference. A region slightly denser than its surroundings pulls in more material. That extra material increases its pull. Over time, contrast grows. Light emerges from collapse. Structure forms from subtle asymmetry. Yet, over the longest stretches of time, gravity's creative phase gives way to something quieter. The universe continues expanding at a rate governed today by roughly 70 kilometers per second per megaparsec. And because expansion is accelerating, galaxies not gravitationally bound to us will recede ever faster. The observable universe, already about 46 billion light-years in radius due to cosmic expansion, will not shrink, but the portion accessible to interaction will effectively contract. Light emitted from sufficiently distant galaxies will never reach us. Expansion stretches space faster than photons can traverse it. The cosmic microwave background, currently at about 2.7 Kelvin, will cool further as its wavelength stretches. Temperature differences diminish. Entropy increases. Gravity still operates, but the canvas changes. Within gravitationally bound systems, however, time unfolds differently. Consider what happens when galaxies merge. In about 4 billion years, the Milky Way and Andromeda will collide and gradually coalesce into a single elliptical galaxy. This is not a violent collision of stars. Distances between stars are vast, but a slow gravitational dance where tidal forces rearrange orbits. Gas clouds may compress and trigger new waves of star formation. For a time, gravity will once again generate brilliance from motion. But eventually, gas supplies thin. Star formation declines permanently. The merged galaxy becomes a stable island of aging stars orbiting a central supermassive black hole. That black hole, perhaps containing billions of solar masses, will quietly dominate the gravitational center. On timescales of trillions of years, even red dwarf stars will exhaust their fuel. These small stars, some with lifetimes approaching 10 trillion years, burn slowly because gravity compresses them gently compared to larger stars. But nothing burns forever. When fusion ends, gravity will compress their cores into white dwarfs. Over unimaginable epochs, white dwarfs cool into black dwarfs, hypothetical objects so cold and faint that none yet exist because the universe is not old enough. Gravity maintains their structure through degeneracy pressure, not fusion. They are relics of equilibrium, supported against collapse by quantum principles. Beyond stellar remnants, gravity's most dramatic structures persist longest. Black holes. Stellar mass black holes and supermassive black holes may outlive nearly every other organized structure. But even they are subject to time. Through quantum processes at the event horizon, black holes emit radiation, losing mass extremely slowly. A supermassive black hole might require around 10 to the power of 100 years to evaporate completely. This number is so vast it renders the current age of 13.8 billion years almost negligible by comparison. Still, the trend is clear. Gravity forms black holes through collapse, and time disperses them through evaporation. Collapse and dissipation bound together. If dark energy remains constant, the large-scale fate of the cosmos is continued acceleration toward heat death. Heat death does not mean cold emptiness alone. It means the absence of gradients. No temperature differences large enough to drive processes. No dense gas clouds left to collapse into new stars. Gravity requires contrast to create structure. Without dense reservoirs of matter, it can only maintain remnants. Expansion thins the medium. Dark energy ensures that distant regions become causally disconnected. In this future, observers within a gravitationally bound galaxy would see darkness beyond their local cluster. The evidence of cosmic expansion might become impossible to measure. The history of the Big Bang would be hidden behind redshifted radiation stretched beyond detectability. Yet the equations governing gravity would remain unchanged. Spacetime would still curve in response to mass energy. Local systems would still orbit according to gravitational geometry. Even in near equilibrium, gravity defines the shape of trajectories. There is also a delicate balance between gravitational collapse and expansion that defines our era. If the density of matter had been slightly higher in the early universe, gravity might have overcome expansion, leading to eventual recollapse, a so-called Big Crunch. If dark energy were significantly stronger, expansion might tear apart even galaxies in a distant Big Rip. Current observations suggest neither extreme. Instead, acceleration continues steadily. Structures already bound remain intact. Structures not bound drift apart. Gravity governs islands. Expansion governs oceans. In this interplay, gravity shapes time at every scale. On Earth, gravity determines orbital periods and thus the length of a year. In stars, gravity sets the pressure that determines fusion rates and therefore stellar lifetimes. In galaxies, gravity determines rotation curves and stability. On cosmic scales, gravity's competition with dark energy determines how long structures persist. Even the measurement of cosmic age, 13.8 billion years, comes from modeling how gravity slows expansion in earlier epochs before dark energy dominates. Gravity is therefore not merely one force among others. It is the framework that determines how time accumulates. Without gravity, there would be no stars to illuminate billions of years. Without gravitational binding, matter would remain diffuse, incapable of complexity. Without gravitational collapse, there would be no black holes to mark the extremes of spacetime curvature. And without expansion, driven against gravity's pull, there would be no evolving cosmic horizon. The long arc of time is not linear emptiness. It is shaped continuously by curvature, by attraction, by equilibrium, and by expansion. From the first 380,000 years when the universe became transparent, to trillions upon trillions of years in the future when only remnants remain, gravity defines transitions. It births structure from subtle differences. It balances pressure and collapse inside stars. It gathers galaxies, creates black holes, and as expansion stretches space toward quiet uniformity, gravity preserves what can still hold together. In that sense, gravity is the thread stitching time across scales, from nanoseconds measured in atomic clocks corrected for gravitational dilation to 46 billion light-years of observable radius shaped by expansion. It is the quiet architect not only of motion, but of duration. If you have followed this journey from the expanding horizon to the fading future, and you are still listening at the edge of cosmic time, gently type 3 in the comments. A small marker that you reached the end of tonight's quiet passage through gravity and the long future of the universe. As we continue further along this immense timeline, gravity begins to feel less like an event and more like a constant presence, a background law that never switches off. In the present era of the universe, about 13.8 billion years after its beginning, we live during a rare transitional phase. Stars are abundant. Galaxies are visible in every direction. The cosmic microwave background still glows faintly at 2.7 Kelvin, detectable with sensitive instruments. Expansion proceeds at roughly 70 kilometers per second per megaparsec, yet gravity still binds clusters, galaxies, solar systems, and planets. This balance between structure and expansion is temporary. Billions of years from now, the sky will look profoundly different. As acceleration continues, galaxies beyond our local group will cross a cosmic event horizon. Their light, stretched by expansion, will fade into wavelengths too long to detect. Eventually, observers in the distant future would see only their merged galactic remnant surrounded by darkness. The evidence of cosmic expansion would not be obvious. The large-scale universe would become observationally inaccessible, even though it still exists beyond the horizon. Gravity will still govern the internal motions of stars orbiting the galactic center. Dark matter halos will continue to provide the gravitational scaffolding that holds the galaxy together. Yet on scales larger than gravitational binding allows, expansion will have effectively won. This interplay reveals something subtle about gravity. It is strongest where matter density is highest. In the early universe, when matter was densely packed, gravity significantly slowed the expansion. Over time, as space expanded and matter diluted, gravity's ability to slow expansion weakened. Dark energy, whose density remains nearly constant as space grows, began to dominate. Today, dark energy accounts for roughly 70% of the universe's total energy density. Matter, including dark matter and ordinary matter combined, contributes about 30%. This shift in dominance determines the long-term trajectory of cosmic time. Still, gravity remains essential for every process that creates complexity. Without gravitational collapse, hydrogen would never ignite into stars. Without gravity compressing stellar cores, heavier elements like carbon and oxygen would never form. Those elements, forged in the gravitational furnaces of stars and released in supernova explosions, make planets and life possible. Gravity is therefore indirectly responsible for chemistry, biology, and memory. It sets the conditions under which time becomes meaningful. In the distant future, after star formation ends, gravitational interactions will still shape the fate of stellar remnants. Over trillions of years, gravitational encounters between stars within galaxies will gradually alter orbits. Some stars may be ejected into intergalactic space through gravitational slingshot effects. Others may spiral inward toward the central black hole. Galaxies will slowly evolve through these interactions, even without new star formation. Gravity ensures that motion never truly freezes. It redistributes energy over vast timescales. Black holes, though often imagined as final endpoints, are part of this redistribution. When two black holes merge, they release gravitational waves, ripples in spacetime carrying energy outward at the speed of light. These waves slightly reduce the total mass of the merged black hole compared to the sum of its parts. Over unimaginable spans of time, such processes subtly reshape gravitational systems. Eventually, when black holes evaporate through quantum radiation, their mass energy returns to the wider universe as low-energy particles. Even in apparent finality, gravity participates in transformation. The concept of heat death describes a state where the universe approaches thermodynamic equilibrium. In such a state, energy is uniformly distributed. There are no large gradients to drive processes. Gravity initially creates gradients by pulling matter together. But once available matter is locked into remnants and expansion has separated structures beyond interaction, gravity's creative potential diminishes. It becomes a keeper of stable configurations rather than a builder of new ones. Yet the laws governing gravity do not weaken. The curvature of spacetime remains responsive to mass energy, however sparse. If one imagines traveling far into this future, perhaps 10 to the power of 100 years from now, the cosmos would be dark and cold. The temperature of space would approach absolute zero. Black holes would have evaporated. Only extremely low-energy particles would drift through vast expanses. Space-time would be nearly flat as mass energy density becomes minimal. Gravity would still exist in principle, but with little structure left to shape, its influence would be subtle. The grand arcs of star formation, galaxy mergers, and luminous quasars would belong to ancient history. And yet, it was gravity that made all of those eras possible. It is gravity that determines stellar lifetimes, such as the Sun's roughly 10 billion-year total span. It is gravity that determined orbital speeds, Earth moving around the Sun at about 29.78 kilometers per second, the Moon orbiting Earth at roughly 1 kilometer per second. It is gravity that governs escape velocities, galaxy rotation curves, and the bending of light around massive objects. Even cosmic expansion is described within the framework of gravitational field equations. Gravity is not separate from expansion. It is embedded within the same geometry of spacetime. What makes this long arc of time profound is not only its scale, but its continuity. From fractions of a second after the Big Bang to trillions upon trillions of years in the future, gravity never switches roles entirely. It transitions. It amplifies density differences. It stabilizes burning stars, collapses massive cores. It binds galaxies, competes with expansion. it maintains remnants, and through all of it, it shapes the passage of time itself. Time flows differently in stronger gravitational fields. Clocks nearer massive objects tick more slowly. Even in an expanding universe, local gravitational wells influence duration. Thus, gravity is not merely shaping space. It is shaping how long processes take, how quickly stars burn, how slowly black holes evaporate. It is the quiet architect not only of motion, but of sequence and duration. The birth of a star, the lifetime of a galaxy, the fading of the cosmic microwave background, the potential heat death of the universe, all unfold within gravity's geometry. Across 46 billion light-years of observable space and across epochs beyond comprehension, gravity stitches events together into a coherent narrative. It links the smallest orbital period to the largest cosmological horizon. If you have followed this final stretch through the distant future, through expansion, collapse, equilibrium, and fading light, and you are still here at the edge of this immense timeline, gently type 3 in the comments, marking that you reached the end of tonight's quiet journey across gravity and the long unfolding of cosmic time. There is one final perspective to consider when we follow gravity all the way to the edge of imagination. Gravity does not merely act on objects within time. It defines the stage on which time itself unfolds. When we say the universe is 13.8 billion years old, we are measuring how space-time has expanded under the combined influence of matter, radiation, dark matter, and dark energy. That number is not independent of gravity. It emerges from solving how curvature evolves. If the density of matter had been slightly higher in the early universe, gravitational attraction would have slowed expansion more strongly, shortening the timeline before possible recollapse. If dark energy had been weaker, expansion might be decelerating today instead of accelerating. The age we measure is a consequence of this delicate gravitational balance. Even the observable radius of roughly 46 billion light-years is not a simple distance but a record of how space-time stretched while light traveled through it. Gravity and expansion together determine the size of what we can see. In the early universe, gravity acted almost immediately after matter formed. About 380,000 years after the beginning, when electrons combined with nuclei and the universe became transparent, slight density variations were already present. Gravity amplified them over hundreds of millions of years, pulling matter into the first stars. Those stars, under gravitational compression, ignited nuclear fusion and began producing heavier elements. Without gravity, there would have been no ignition threshold reached, no pressure sufficient to raise core temperatures to millions of degrees. Every luminous point in the sky owes its existence to gravitational compression. Yet gravity is patient. It works over vast timescales. A massive star may live only a few million years because gravity compresses its core intensely, accelerating fusion. A smaller star like the Sun, balanced more gently, lives around 10 billion years. A red dwarf may live trillions. Gravity determines how quickly nuclear fuel is consumed. In that sense, gravity controls stellar clocks. The lifetime of a star is a gravitationally tuned duration. On galactic scales, gravity organizes rotation. Stars orbit galactic centers at speeds determined by the mass distribution, much of it dark matter. The existence of dark matter itself is inferred through gravitational behavior. Galaxies rotate too quickly at their outskirts to be held together by visible matter alone. The additional gravitational influence shapes the stability of cosmic structure. Without that hidden mass, galaxies might have dispersed long ago. Even the cosmic web, vast filaments of galaxies stretching across hundreds of millions of light-years, exists because gravity gathered matter along invisible scaffolding. And still, gravity's influence does not override everything. On the largest scales, expansion dominates. At about 70 kilometers per second per megaparsec, space stretches in proportion to distance. Beyond gravitationally bound systems, this stretching wins. Over billions of years, galaxies outside our local group will fade beyond reach. Their light will redshift, wavelength lengthening as space expands. Eventually, even the cosmic microwave background, now at 2.7 Kelvin, will cool so much that it becomes undetectable. Future civilizations, if any remain, might see a dark sky with no trace of the Big Bang's afterglow. Yet gravity will still govern their local motions. Planets will orbit stars if any remain. Remnants will orbit black holes. Curvature will still define trajectories. In the era approaching heat death, gravity does not disappear. It simply has less raw material to shape. Most stars will have burned out. Stellar remnants will cool. Black holes will slowly evaporate over inconceivably long durations. Expansion will have separated gravitational islands so completely that interaction between them becomes impossible. The universe trends toward maximum entropy, where energy differences flatten and no further large-scale work can be done. Gravity initially created the gradients necessary for structure by amplifying unevenness. Over time, those gradients dissipate. But even in equilibrium, gravity remains encoded in spacetime geometry. It remains the rule by which mass and energy curve existence. There is a quiet symmetry in this story. Gravity begins by shaping the first clumps of matter from a nearly uniform plasma, creates stars that shine for billions or trillions of years. It collapses massive cores into neutron stars and black holes. It binds galaxies against expansion locally. And in the end, as expansion stretches the cosmos thin and cold, gravity preserves what remains until quantum processes slowly erase even the densest objects. Throughout this entire arc, from less than 1 million years after the beginning to perhaps 10 to the power of 100 years in the future, gravity is continuous. It is the thread stitching epochs together. It is present in the fall of an apple at 9.8 meters per second squared and in the merging of galaxies separated by millions of light-years. It governs orbital speeds like Earth's 29.78 kilometers per second around the Sun and recession speeds of distant galaxies carried by expansion. It shapes the bending of light near massive objects and the stretching of wavelengths across cosmic distances. Gravity does not shout. It does not flash like a supernova or roar like a quasar. It works quietly, persistently, bending space, slowing time near mass, defining the duration of stars, and setting the long rhythm of the cosmos. Without gravity, there would be no structure to measure, no clocks to tick, no cycles to count. Time itself would lack anchors. In that sense, gravity is not only a force or a curvature. It is the quiet architecture that allows events to unfold in sequence. From the birth of the first star to the fading of the last black hole, gravity shapes both motion and memory. It binds beginnings to endings. And as you sit here now, on a small planet orbiting an ordinary star in one galaxy among billions, gravity is still guiding the Earth in its orbit, still bending spacetime beneath your feet, still stitching this moment into the vast continuum of cosmic time. If you have traveled through this entire arc, from expansion to equilibrium, from stellar birth to cosmic fading, and you are still listening at the edge of the universe's long story, gently type 3 in the comments. A small confirmation that you reached the end of tonight's quiet journey through gravity and the future of time.